In this video, we consider the mechanism of the Fischer Esterification reaction, which is the process by which we make an ester from a carboxylic acid and an alcohol under strongly acidic conditions. As we will see, this reaction is the exact reverse of the acid-catalyzed hydrolysis of esters that we considered in the previous video. Okay, so as our net reaction here, we're going to use methanol as the solvent and the alcohol nucleophile, and we're going to turn a carboxylic acid into its methyl ester. Water, of course, is kicked off as the byproduct. Okay, so this mechanism should look very familiar. It is the exact same mechanism we looked at on the previous slide, only in the reverse direction. So being an acid-catalyzed mechanism, there are going to be proton transfers at the beginning, in the middle, and the end of the mechanism, bookending the nucleophilic attack followed by elimination later on in the mechanism. So the first step is using acid to protonate the carboxylic acid. So as I mentioned in the last video, even though carboxylic acids are thought of as acids, they can still be protonated on the carbonyl oxygen, just like any other carbonyl compound can be protonated on the carbonyl oxygen. So the acid that's used in this case is CH3OH2+. You are using methanol as the solvent for this reaction. We'll talk about why at the end of this video. But when you take a drop of strong acid, such as sulfuric acid, put it into methanol, what gets generated as the acidic species in solution is CH3OH2+. This is going to protonate the carbonyl oxygen to generate the protonated carboxylic acid. It's a proton transfer reaction requiring the usual 2 arrows. This is going to be an equilibrium process with an equilibrium constant of about 1, because once again we're starting with an oxygen with 3 bonds and a positive charge. We are ending with an oxygen with 3 bonds and a positive charge. Okay, but the reason why we needed to protonate the carbonyl oxygen, just like in every other such reaction we've looked at under acidic conditions, is to make the electrophile more electrophilic. That will lead it to be more susceptible to nucleophilic attack by a weaker nucleophile, which is what in fact happens. Methanol is the nucleophile that attacks the protonated carbonyl by forming a bond from the oxygen to the carbonyl carbon and breaking the CO pi bond, putting those electrons onto the oxygen. Methanol is a good enough nucleophile in this case because the carbonyl has already been protonated. You do not have any better nucleophiles than methanol present because this reaction is taking place under acidic conditions. So there's no nucleophiles present that have negative charges. Okay, so now that leads us to the second intermediate here, where we have the methanol has come in. The oxygen still has its positive charge and still has the hydrogen on it. So now, in order to make an ester, one of the 2 OHs has to be converted into a leaving group, and we're going to do that through 2 proton transfers. One where a solvent molecule methanol is going to come in and remove the hydrogen from the methanol molecule that just came in as a nucleophile. That will leave a neutral intermediate, and then that intermediate will protonate on the OH using CH3OH2+ as the acid. Of course, the point of protonating on this OH is to convert it into a better leaving group. Once again, just like in the reverse mechanism, this proton transfer reaction can be carried out intramolecularly. You can have the proton go directly from the CH3O to the OH, gets you to the same point in 1 fewer steps. Okay, so now that we have an OH2+, it's a good leaving group. It's going to want to leave as water. So loss of the leaving group is the next step of the mechanism. And just like in all of these other mechanisms, expulsion of the leaving group occurs at the same time as regeneration of the carbonyl CO double bond by taking the electrons on the OH and using them to form the CO pi bond. This leads us now with a protonated ester, and that protonated ester is deprotonated using methanol, that is the strongest base present in solution under these acidic conditions. And that methanol comes in, removes the proton, and gives you the neutral ester, and regenerates CH3OH2+, the acid that we used in the first step. Okay, so this is an equilibrium process. It is the exact reverse of acid-catalyzed ester hydrolysis. The way we push this equilibrium to the right is we use a large excess of alcohol as a solvent. And in fact, if the alcohol that we want to use has a high boiling point, if it's pentanol or hexanol or something big like that, you can actually set up this reaction as a distillation by distill off the water that you remove as a byproduct, and that will also push the equilibrium to the right as well. Alternatively, we have looked at other methods of removing water, like using a drying agent in the reaction that can remove the water as well. Okay, so now in the last couple of videos, we've looked at the same mechanism backwards and forwards: acid-catalyzed ester hydrolysis, acid-catalyzed ester formation from a carboxylic acid.